limit. Pretty easy, but they bring back limits in the middle of chapter 3. Now, the reason why is when we get to 3.6, we're going to have to remember some things about limits. So that's why we've got this kind of thrown in there. But it's not deriving like we had been doing all before break. So here's the equation I'm going to have us put into our y equals in our calculator. We're going to graph the function 3x squared divided by x squared plus 1. We're going to look at that graph in our calculator. Now, this doesn't have what to do with what we're doing today, but any words come to mind on how to describe the picture of that? Do you remember any key words? It's a cusp. Yeah, like that bird in the sky when you're drawing your pictures. So this is a cusp, even though that's not really what we're looking at today. We are looking at limits. So here's what I want to have you look at with this graph. As we look at this graph and we're going to the right, and we're going to go to the right forever, we want to know the limit. Now remember this about limits. They are the y values. So as you go right forever and forever and forever, what y value is the graph approaching? Any ideas? 3. Okay. Other direction. As we go left forever and forever, what y value is that approaching? 3 also. These are how we're going to do limits with infinity. So how this will look is what I just asked you. The limit of the function as x approaches infinity. So this is as we go towards infinity, so as far as we can go to the right. Limits are all about the y values, and you told me it was approaching 3. How this will relate to pre-calc? Do you remember talking about end behavior last year? This is finding our end behavior. So as we're going forever and forever to the right, what's our end behavior? Well, it's approaching 3. Then the other question I asked you, this is what it means. The limit of the function. And then I asked you as we were going towards the left forever and forever, so that's negative infinity. And that equals 3 as well. So now, instead of focusing on a certain x value, we're looking at the ends, and we're going to see what y value that might approach. Do you think there's ever going to be the possibility that this kind of limit won't exist? Sure. Just think about like y equals x. Doesn't that go up forever and forever? It's not going to stop at a y value. As it goes to the negative infinity, it's not going to stop at a y value. So just like before, we're going to have limits that don't exist. But if they are approaching a certain y value, then we will have a limit. Okay, let's do some properties. Yes, Julie. Oscillating. Like the, well, so in between, like, so here, when it's oscillating, it would not. But if we looked back at that graph, the ends actually did approach a number. They kind of like, I think if I remember right, they go towards like the x-axis. So their end behavior would be approaching 0. But in the oscillating part, there wouldn't be a limit. Does that answer what you're asking? Okay. Okay. All right, properties. And these properties are going to work if the limit of f of x as x approaches either plus or minus infinity and the limit of g of x as x approaches plus or minus infinity exists. So this is the condition. For these following properties to work, the two limits for these functions has to exist as we're looking at their end behavior. Okay, so here's the first one. If we are asked to find the limit as x approaches plus or minus infinity of f of x plus or minus g of x. So remember, that could be like x squared plus 7, the sine of x minus 4, x cubed minus 2x squared. So if we have those two functions added or subtracted, we've actually done this property like every time we've learned something new. Any ideas what this is going to tell us we're allowed to do? Yeah, separate them and find the limit of each of them on their own. So it's the same as finding the limit of f of x and then adding it or subtracting to the limit of g of x. Probably the most annoying thing for this whole section is the time it takes to write all the symbols. Okay, then the second one, and there are only two. The second one says this. The limit as x approaches plus or minus infinity of f of x times g of x. So two functions being multiplied. And we are allowed to just find the limit of each of them separately and multiply them together. So this was also a property back in chapter 1. We just weren't approaching infinity then. So we'll see that at play, but it should come kind of natural to us because we already have done these kinds of things before. But this is just saying that it's allowed. All right, now next thing we're going to do, we're going to write a little statement in math jargon and bring another word into play. And this you talked about in pre-calc as well. If the limit of f of x as x approaches plus or minus infinity and then the way that it's written it in like the technical theorem, they put equals L. And what they mean by that is it equals some number. So they're saying that it exists and it equals a constant and it equals something. So if we find our limit and we get an actual answer to it, then y equals L is a horizontal asymptote. So we have talked about vertical asymptotes since the very first week of school. but we haven't really talked about horizontal asymptotes. So if we think back to that graph that I had you graph just a couple minutes ago, remember how you told me that the answers to both of those were 3? Is there a horizontal asymptote at y equals 3? Yeah. So in this section, every answer that we get is actually 2 answers. It's the answer to what the limit is, and it's also its horizontal asymptote. Every answer we have. So if the limit equals 10, there's also a horizontal asymptote at y equals 10. If the limit doesn't exist, then it means there's no horizontal asymptote. So we have a lot of horizontal asymptotes popping up. And that's actually why they put this section in the spot that they did. Great question. Give me about 5 minutes and I'll answer it. Okay, next little part, we're going to do a theorem. It doesn't really have a name in the book. It's theorem 3.10. That's not important. But this is a little theorem to go with what we're doing. And here's what we're going to do for the theorem. The limit as x approaches plus or minus infinity of c over x to the r. Okay, we're going to figure out what this should equal, and we're going to think about it logically. Okay, c stands for some constant. R stands for some rational number. We're using x values to approach infinity. So if we think about that logically, these x values are getting bigger and bigger and bigger. The constant and the rational number are staying the same. So think about these fractions where the bottom gets bigger and bigger and bigger. 1/10, 1 100th, 1 1,000,000th, 1 1,000,000,000th. As the bottom gets bigger and bigger and bigger, what's happening to the overall value of that fraction? It's getting smaller. And since this is a limit, it's approaching 0. So this is actually really nice, and this will help us answer Toby's question here in just a minute. If we ever have a fraction in this form, and they're asking us this limit question, it's going to be 0. So this could look like a lot of different things. This could be 5 over x to the 10th. It could be 10 over x to the -4th. It could be 14 over x to the 300th. So as long as we have it in this form and we're finding the limit, we know it's going to be 0. Okay, so we're going to find that helpful here. Okay, now for this next part, we're going to actually do some numbers, and we're going to try to put these into practice. So we're going to find the limit as x approaches infinity of 5 minus 2 over x squared. And we're going to use these properties and work through this one. Okay, so first thing I noticed, there's a minus sign, and the first property says that I can split it up. Now, I am going to take the time to show that. You know how we get faster at this, and a lot of times you skip steps, which is fine. I'm going to write all the steps out right now, just so we're comfortable, but you'll be able to do most of these in your head in a little bit. So I'm going to split it up into 2 limits. They're both approaching infinity. Okay, now for that first limit, we've got to remember back from chapter 1, when we have the limit of a constant, what does that equal? That constant. And here's the reason why. 5, that's the equation, y equals 5. So that's your horizontal line, y equals 5. No matter where you go, what's your y value? 5. So this is our limit, 5, minus Is this in that form of that theorem? Yeah, so that means it's 0. So then overall, this limit is 5. If we graphed that function, we would see as we go to the right, the end behavior is approaching 5. Is there a horizontal asymptote? Yeah, y equals 5. Okay, let me show you this next one. Let's find the limit as x approaches infinity of 2x minus 1 over x plus 1. Okay, here's where we're going to have to pull some math magic. Because when I split this up, even if I split it up and did like the limit of 2x minus 1 and divided it by the limit of x plus 1, I still don't have just like a constant or something that's in the form of that theorem. So I'm going to do something that you're going to think is really strange, but I'll explain it after it happens. I'm going to multiply the top and the bottom by 1 over x. Now, since I'm multiplying the top and the bottom by that, it's not going to change its value. It's just going to change what it looks like. So I'm not messing with what it actually is. I'm just messing with how it looks. So I'm going to distribute. So 2x times 1 over x is 2 minus 1 over x times 1 is 1 over x. And then I'm going to distribute down here. X times 1 over x is 1, plus 1 times 1 over x is 1 over x. Okay, now, if I took the limit of each of those parts, what's nice about each of those parts is they're either a constant or they're in the form of that theorem. So now I'm going to take the limit of each of those parts. So then the limit of 2 is 2. The limit of 1 over x, so that's our theorem, that's 0. The limit of 1 is 1. The limit of 1 over x is 0. So then that gives me a 2. The limit is 2. The horizontal asymptote is 2. Okay, now let me go back and tell you why I did that. So the way that I was able to get it into a form that I could use, I multiplied by something. And I had to multiply by something that would get us either all fractions or constants. So the goal is, out of all the things, we're going to find what the highest degree is. So this x to the first, that was my highest degree. So I'm going to multiply by 1 over x, and then I'm going to put whatever highest degree is there as my exponent. And that'll get it into the form that we want. So we're going to practice that, because this is the part on the AP test where you're going to have to find the limit, and they're going to break out that word justify, and we're going to have to know how to show all of this. So for this next part, I've got 3 questions. They're all very similar, but they're different in one way. And we're going to look at these 3 questions, and then we're going to kind of try to come up with some rules that help us out. So here's the first one in this group that kind of goes together. The limit as x approaches infinity, and it's going to be 2x plus 5 over 3x squared plus 1. Okay, so it's not all in the form where we can take the limit of each of those parts. So then you look at all of the components. What's our highest degree? Yeah, so what we're going to do is we're going to multiply the top and the bottom by 1 over x squared. And then we'll distribute that through to everything. We'll have 2 over x plus 5 over x squared, all divided by 3 plus 1 over x squared. Okay, out of those 4 different terms, are they either constants or in that form from the theorem? Yes. So now I can take the limit of each of them. Well, I'm going to have 0 plus 0 over 3 plus 0. That's 0 over 3, which is 0. So our limit for this is 0. Does this have a horizontal asymptote? Yeah, at y equals 0. Okay, so that's one of the 3. Second one, we're going to do the limit as x approaches infinity. We're just going to tweak this a little bit. 2x squared plus 5 over 3x squared plus 1. Okay, out of all those 4 degrees, or 4 terms, what's our highest degree? Yeah, so we're going to multiply by 1 over x squared, top and bottom. We'll get 2 plus 5 over x squared. In the denominator, we'll get 3 plus 1 over x squared. And we know we're in good shape because they're all either constants or that special fraction. And then we'll take the limit. 2 plus 0 over 3 plus 0, which is 2/3. So the limit is 2/3. There's also a horizontal asymptote at 2/3. All right, last special type. The limit as x approaches infinity, tweak it just a little bit, 2x cubed plus 5 over 3x squared plus 1. Highest degree overall? 3 now. So now because 3 is our highest degree, we're going to multiply the top and the bottom by 1 over x cubed. That'll give us 2 plus 5 over x cubed. Then in the denominator, 3 over x plus 1 over x cubed. And then they're all in the form that we want, so we can take the limit. 2 plus 0 over 0 plus 0. So then that's 2 over 0. So that's undefined. So this limit does not exist, and we don't have a horizontal asymptote for this one. Okay, so as you're looking at those, right now, before I go any farther, any questions about any of that part? Okay, what we just did is we actually proved a set of pre-calc rules from last year. There was a set of rules about horizontal asymptotes that you just were kind of given the list to, and this is the reason why. And so there are 3 types of answers: 0, some kind of other number, or undefined. So let's think about where those relate and how we can know from the original. So here, if you look at just the equations, what's changing in those equations? Yeah, so in this one, the highest degree is in the denominator. Whenever the highest degree is in the denominator, your answer will be 0. Here, the degrees were equal. So whenever you have equal degrees, you're going to do leading coefficients, whatever that might be. And then here, the highest degree is in the numerator. So whenever you have the highest degree in the numerator, the overall answer does not exist. Do those rules kind of sound familiar? But now in calculus, since we know limits, we can do the y. So I'm going to write out those rules so we have them in our notes, but it's nice. Now, I've got good news and bad news. Let me tell you the good news first. Good news is, could you just look at a function and now know what the answer is? Bad news, in this section, you have to show all of your work because we've got to practice showing the justifying. But after this section, I'll let you use the shortcut rules. So this section, we have to show all of that extra work, but after this section, you can use those little rules to help you out. Okay, so let me write those rules out so we have them in our notes, and this will help us know our answers. So first one, if the degree is higher in the denominator, the limit / horizontal asymptote is 0. Okay, then our second situation, if the degrees are equal in the numerator and denominator, the limit / horizontal asymptote will be the leading coefficients. And I'll write our third one up here. Degree is higher in the numerator the limit / horizontal asymptote does not exist. So these rules will be very helpful. You'll be able to tell just by looking at the function what the limit is, what the horizontal asymptote is, based on these degrees. And again, this section only, which is the short section anyways, we have to show the work to get there. Okay, now there's one more thing we have to add into this lesson, and it throws a little curveball. What makes this really fun is if we get square roots in the mix. So that's what we're gonna do next, show you a couple things with square roots. Okay, so let's look at this one first. The limit as x approaches infinity of 3x minus 2 over the square root of 2x squared plus 1. Okay, in the numerator, what's our highest degree? 1. In the denominator, what's the highest degree? 1, because you're square rooting an x squared, so it's still 1. So the degrees match. So again, we could use our rules, but to show this, the numerator, I'm going to multiply by 1 over x. The denominator, I'm going to multiply by 1 over the square root of x squared. These are the same, but technically, when we multiply square roots, we have to have matching square roots together to combine them. So even though these are equivalent, we're showing that we're using our square root rules. Because of the plus sign. All right, so distributing through, we'll have 3 minus 2 over x. Okay, now, just a little review of your square roots. So this is technically this. When I multiply that through, you're allowed to put one big square root over it. And then from there, you can divide both of them by x squared. So this is all the stuff that's allowed with your square root. So again, if you want to write out all of these steps, you can, but we could jump right to this. But that's all the background work that's going on with that square root. Questions to get to the blue part. Okay, then in the blue part, everything's in a good form. Everything's a constant or in that fraction. So if I take the limit of that, I'll have 3 minus 0 over the square root of 2 plus 0, which is 3 over the square root of 2. So that's our answer. That's also our horizontal asymptote. That wasn't horrible, was it? Okay, let me show you this next one. Find the change. Well, approaching negative infinity. Okay, so when you learn square roots, like x squared equals 4, what is the right way to solve for x squared equals 4? Back in algebra 2. Square root both sides and plus or minus. Okay, so this is what is going to come into play. We've got our square root. Because this is approaching positive infinity, it's the positive part of our answer. This is approaching negative infinity, so it's the negative part of our answer. Here's where it's going to show. When I multiply, I'm going to multiply by 1 over x and negative 1 over the square root of x squared. Why does that seem wrong? These aren't the same, are they? So technically, I'm multiplying by negative 1. But the reason I'm doing that is because it's the negative part of my answer. So then I'm going to go through, do everything the same, but my final answer will be negative. So then I'll have 3 minus 2 over x In the bottom, I'll have a negative square root of 2 plus 1 over x squared. That'll give me 3 minus 0 over negative square root of 2 plus 0. And so my answer will be 3 over negative square roots of 2. So square roots, just like x squared equals 4, you get x equals plus 2 and minus 2 as an answer. Depending on what infinity you're approaching, you'll get a different answer. Now, I want us to look at this so you can kind of visualize what's going on. So let's take our calculators and put this function in there. Because square roots always give us a kind of a weirder looking graph. And so hopefully when you graph it, as you go towards the right, is it a positive y value that you're approaching? Yeah, and then as you go to the left, it'll be a matching y value but the negative of it. And so for square roots, we're always going to have this kind of looking graph when we have this kind of function. And as you approach infinity, it will approach one value and negative infinity the other.
So I understand the math, but I know that you multiply by a negative because x is approaching negative infinity, but why can't we do that?
Because whenever we solve for a square root, we have to put plus or minus. So we're just doing plus or minus here and here.
So, okay, so that's why the numerator value is multiplied by the numerator, isn't it?
Yes, yes, yep. Great, that was what I was gonna ask next. Okay, so let's say we have a negative up here. What's gonna end up happening is this final answer will be negative. But then what will happen here? If we have a negative here, the final answer will be positive. So it could be that as you're approaching positive infinity, the answer is negative, but that just means as you're approaching negative infinity, the answer is going to be positive. And we'll have lots of time to kind of play with that tomorrow. I'm going to give you lots of different square roots to work with. But that's 3-5. Tomorrow we'll just practice this. I'll give you all kinds of scenarios and we'll get ready for this. All right.